Assalamu alaikum, dear students. Welcome to the lecture of the modern physics. Last time we were discussing the solutions of the Arthur Beiser books for the first chapters, and we have solved the exercise problems up to question number 6. In this session, we will start from the question number 7. The first question says that how fast most spacecraft travel relative to the Earth for each days on the spacecraft to corresponding to 2 days on the Earth. So we are given that spacecraft which is traveling with a high speed relative to the Earth for each day on the spacecraft to correspond to 2 days on the Earth. It means we are given with the time dilation effects. So the difference between these two planets or the two frames are related with the time dilation formulas. If I write this T, which is equal to T naught over 1 minus V square over C square. Here we are given how fast most spacecraft must travel. It means he is asking the speed of the we have to find the speed, and relative to the earth for each days on the spacecraft to the corresponding to 2 days on the earth. 2 days on earth mean this is 2 and this is 1. So if we cross multiply these fractions, so this will become 1 over 2 is equal to 1 minus V square over C square, and that now we have to solve this equation for V. We will square this on both sides and solve it for V. So we will definitely obtain V is equal to under root 3 over 2 and C, which is 2.60 cross 10 power 8 time. So this is our required answer. In question number 8 says that the Apollo 11 spacecraft that landed on the moon in 1969 traveled at a speed relative to the earth of this. This is the speed of that spacecraft. He is talking to an observer on the earth how much longer than his day was a day on the spacecraft. Again, this is a time dilation effect. We are given with the speed v is equal to this, and t is equal to t naught over 1 minus v square over c square. So here this is the technical portion of the question. To an observer on earth how much longer than his day was a day on the spacecraft. So we have to find the time for the moving spacecraft. So this is time for moving spacecraft. T is equal to, and for what, 20 for 1 day it means 24 hour. 24 hour over 1 minus v square over c square. So we will put this v here and we will get definitely some answer. You can put these values of v and c. C is equal to 3 cross 10 power 8 meters per second. If we look for the question number 9 and I zoom it says that a certain particle has a lifetime of this second when measured at rest. It means we are given a lifetime. Rest means rest mass time. How far does it go before decaying if its speed is 0.99 c when it is created? So the lifetime of the particle is t naught when it was at rest, and the distance to the particle will travel is, so we relate both expression for time and multiply with v. So this will give us the distance. Here this is a time, and if we write the time dilation formula, t is equal to t naught over 1 minus v square over c square. If we multiply v this on this side and on this side, so this is vt and this is vt naught. So we are given with the v, and we are given with the t naught and 1 minus v. So we are given with the v 0.9 c and c. So this is the length, or the how far means he is asking for the sum about length. How far means it is the distance. So vt is the required distance which he said that particle will cover before decaying. So vt naught, v is 0.9 c and t naught is this, and 1 minus v square over c square. So this will give us 210 meters. If we go to question number 10, which say that spacecraft descending from the earth at this speed 0.97 transmit data at the rate of this 1 cross 10 power 4 pulse. At what rates are they received? So we are given with the speed of a radio signals, or any signal where we are talking about. V is 0.97 c, and we are given with the pulse transmission rate, means this is number of pulse. Rate means number of pulse per unit time, which is the frequency. Frequency of the source is 1 cross 10 power 4. And what rate they are received? It means we have to find the observed frequency. We are given with the source frequency and spacecraft descending from the earth. It means if we write the formulas here, I will write it. F is equal to F naught into 1 minus V over C over 1 plus V over C. This is source frequency. Frequency when our source is at rest. This is the frequency, and this is the relative frequency, that the observed frequency here is at what rate they are received. It means this is the observed frequency and this is the frequency of the source, which is given with 1 cross 10 power 4 pulse. Number of pulse per unit time. This rate is, that is number of pulse per unit time. So F naught is 1 cross 10 power 4. If I go back to the formulas, this F is equal to F naught 1 plus V over C and 1 minus V over C. So we are given with the speed and we are given with the F naught frequency at rest. So this will give us the F, which is the observed frequency. If you put the value of V here in this in the bottom and in the top of the expression, and here F naught, so we will get the values of that frequency. Similarly, question number 11. A galaxy in the constellations Ursa Major is receding from the Earth at this speed. If one of the characteristic wavelength of the light the galaxy emits is this, what is the corresponding wavelength measured by astronomer on the Earth? We have to find the wavelength at the rest frame, and we are given with the wavelength in the moving frame. In this question, if we try to write the given data, this is the speed of that galaxies, this is the wavelength of the galaxy which is moving, and we have to find the observed wavelength from the rest frame, which is the Earth. So lambda is equal to C over mu, and if we multiply this with mu naught over mu naught, so this will sum like on what? C mu naught over mu naught into mu, and this is, if we directly write this formula, lambda is equal to lambda naught 1 minus V over C and 1 plus V over C. If we write this frequency term like C over lambda is equal to, and this frequency is C over lambda naught, and this 1 plus V over C and 1 minus V over C. So this C will cancel with C, and we can find this expression for lambda. Lambda will be equal to lambda naught 1 minus V over C and 1 plus V over C. Again, we are given with the lambda naught, which is this, and we are given with the speed V, So we can find the V over C for this expression, and V over C will be equal to minus 0.050, and we can if we plug these values into this expression, this will give the observed wavelength, which is 578 nanometer. This wavelength will be observed from the rest frame, which is the Earth. If we go back to the question 12, which say that frequency of the spectral line in light from a distant galaxy are found to be two-thirds as great as those of the same line in the light from a nearby star. Find the recession speed of the distant galaxy. Again, we will use that formulas and find the expression for the speed. So F is equal to F naught, 1 plus V over C, and 1 minus V over C. So F is given two-third means 2 over 3 times F naught. So this is F naught, and this is 2 over 3 times F naught, because this is given 2 over 3 two-third, and F naught 1 plus V over C and 1 minus V over C. So this F naught will cancel with the F naught, and we will definitely square on the both side. So this will become 4 over 9 is equal to 1 plus V over C and 1 minus V over C. If we cross multiply it on the both side, we will find the recession speed in term of C. So this is a required answer of this question. At this question I will stop my lecture, and again we will try to solve onward questions in the next lectures.